Good morning, class. Can you hear me?
Good morning, Dr. Ken.
So I have recorded this session, and please let me know. If you have any question during this my lecture, okay, you can stop me anytime. So please let me know. Okay, whether you can see my slide. Wait. Can you see my slide?
Yes, Doctor.
Okay, thank you.
Yes.
So yeah.
Yes.
Okay, so if we just quickly look at what we are expected to learn, okay, for this stiffness method, okay, so you have actually learned on identifying the constraint and unconstrained degree of freedom, and there will be a shared video later, okay, from other class on how to formulate the member stiffness matrix, displacement transformation matrix, and force transformation matrix, okay, for these structures. So please visit that video. I hope to get it shared by maybe end of this class, okay, for this video, okay. And then today we are going to directly look at the whole process of this stiffness method on how to apply the local and global stiffness relations, okay, in solving this deformation and also forces, the objective number 3, okay, for our beam example. Okay, so today we are going to look at one of the example. Okay, in my next class, um, I will try to share with you, okay, another example, a recorded video on example number 2. Okay, then I expect that by tomorrow we can do a hands-on tutorial on as I post in the I discuss, or in the compile problem and solution that you have obtained. Okay, I have posted in the chat room the other day. So today we are going to look at the example 1 for the beam. Okay, so I have extracted from the PDF file into this PPT. Are you able to see this example beam 1?
Yes.
Okay, thank you.
Yes,
So,
Doctor.
yeah, please let me know if you don't understand the step or need me to explain again, okay? So, we are going to look at this example 1 today. Make sure you understand the whole process. So, if you look at this example, okay, you can refer to your handout, okay? Let's understand this problem about. So this is the 2-span beam, and it is loaded uh, a concentrated load 48 kilonewton at span BC, and UDL 32 kilonewton per meter acting at this member AB. And the given flexural rigidity E, Young modulus, and the moment inertia has been given to you. Okay, so please make sure you are able to convert this, okay, into we're going to use a kilonewton and meter in the units. Okay, and there are two problems here. You need to first determine the unconstrained degree of freedom and all the support reactions. What is that means? Okay, so meaning that you are going to determine the displacements, okay, the unknown displacement here, and all the support reactions. Okay, then the second one is, please determine the shear forces and bending moment at joint B. Okay, or no S maybe. Okay, at joint B if support C settle 2 mm, meaning that the displacement at C right now has a value of 2 mm instead of 0. Okay, so once you have make sure, consider all this scenario, okay, we can start on the notation. Okay, so please ignore the steps here. Maybe you in your handout also you can take out the steps. Okay, of course we will always start with the notation. Okay, but the remaining of the steps you can start which step first appropriately. Okay, so it is not necessarily following these guides. Okay, as you say, it is only a guide. Okay, so now let us start with the notation. If you look at this problem, okay, what I advise you to do is you draw your support reaction first, okay, to know where is the non-displacement. Okay, for example, I will draw it now. So for fixed support, you are going to have AY, okay, you are going to have AX, you are going to have MA. So at this direction, the displacements will be known as 0. Okay, so meaning that this direction, let's say delta A at vertical. Okay, maybe you just use Y. Okay, and the delta, okay, A at the horizontal, or you put it as X, and also the rotation are all equal to 0. Okay, unless it has a given, you know there is some value for this displacement at that point. So I move to B. Okay, so this is By. So associate with these support reactions at this direction also, the By is equal to 0. Okay, but the Bx and the rotation, okay, will be equal to some value. Okay, but we don't for beam we don't have this we don't really look at the x direction. Okay, because it is very insignificant value. Okay, so at C we have Cy and we have delta Cy equal to 0. So now once you have identified the non-displacement, so we need to know that which one is the non-displacement and the unknown displacement, right? So unknown displacement also named as unconstrained. Sorry, unknown displacement also another term is unconstrained DOF, degree of freedom. So the other one is the non-displacement will be the constraint, okay, DOF. So now the one that if you can see that we will have this the drawn arrow here is all the non-displacement equal to 0. Okay, the unknown will be the one not highlighted here. So what you can do, okay, now is to give a note to the support. Okay, so here there are 3 supports, A, B, C. So we have to put a note here, A, 1, 2, 3. So if there is any difference in terms of EI, okay, there is no. Okay, the EI is constant. So you no need to put extra notes. Okay, then you put in your element. Okay, between the nodes, there are 2 elements here, 1 and 2, and you have to put in the arrow, okay, to address which one is the near end and which one is the far end. Okay, then you need to draw the DOF, okay, arrow. Okay, so for beam, there will be always, okay, a revision here, there will be always 2 DOF per node. Okay, and the DOF direction will be this. Okay, so you need to put at each of the node this okay, arrows. Okay, so you put it here. If you can see that the arrow at node 1, 2, 3. Then you need to give a number it. The rules here is, okay, you need to number the unknown displacement first. Then you name the known displacement. So if you can see that number 1 and number 2 is not drawn in any of these uh, 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 displacements, the non-displacement category. So these are the unknown, okay, displacement 1 and 2 only. Okay, then you can name the remaining of this arrow, yeah, as your preference. Okay, so the 3, 4, 5, 6 will be the non-displacement. You can, I put it here so that you are getting clear. Okay, 3, 4, 5, 6 is the non. Okay, 1 and 2, we don't know the value. And this 3, 4, 5, 6, we know that is 0. So once we have identified these all the nodes, elements, near and far in, the DOF, then we can move to writing the vectors. Okay, because we already have the inputs here. Okay, so for example, the Q, okay, just this is a force vector. Okay, sometimes they call load vectors. Okay, so this, okay, just to make a revision again, Q will be associated with the support reaction. Or the loading. I will put it here, nodal. Okay, meaning that at the nodes only. Okay, whenever at the member, it is not fall under Q. Okay, this is only at the node only. Okay, so if you look at this problem here, figure B1, okay, you have the support reactions, okay. Okay, the drawn here is your support reaction. Of course, you have AX, but in this context, we don't study that. Okay, so therefore, the one that I highlight here, 4, 4, 3, 5, and 6 are all the support reaction. Okay, so you can put it here Q3, Q4, Q5, Q6. You don't know the value. The support reaction we need to determine, right? But at this number 1 and 2, there are no support reaction. Okay, then you need to check whether you have any of these loading at the nodes or not. Okay, in this case, they are known. Okay, so Q1, Q2, you can have a 0. What if, okay, I have 48 kilonewton acting at A, vertical. Class, can you help me? What if I have another 48 kilonewton acting at A, vertically, downward? What shall I do for my Q?
Q4.
Yes,
Q4 40.
yes.
48.
So you shall have I just put it the other side. What if, okay, 48 kilonewton additional on point A, okay, downward. Okay, maybe I put it downward here on point A. So your Q4 now will have a value of Q4 minus 48. Okay, why still have Q4? Because there is AY there. The support reaction is still there. Only there is also a loading there. Therefore, you need to sum up these two these two criteria. Okay, I hope you understand. So now let's move to the displacement. Okay, so displacement we are already identified earlier. Okay, D1, D2, this one, 1 and 2, we don't know the value. So D1, D2, you put it as an unknown. And the rest you know that it is 0. Okay, so if you look at the problem just now, if support C settle to mm, okay, so what are you going to, update your vector of displacement vector D? If support C settle to mm, class?
The D6.
Yes, D6 will have value of 2 mm. Yes, thank you very much. Okay, so I think you are following well. So therefore, D6 will have what is the value? Huh? Class? Positive or negative?
Negative.
Yes, so it will be negative 0.002, right? Yes, meter. Okay, so this is how you update if you have this different scenario. Okay, but now we are going to base on this, okay, because our problem is only having this. So, okay, so this is the one that maybe new to your class, okay, but you can visit the video as I have mentioned, okay, on what is this about, okay, but today we are going to see how to apply this, okay. For beam structure, okay, you are going to determine this member stiffness matrix, okay. So if you open the appendix that I have shared with you, can you see my appendix?
Yes. Doctor.
Yes, yes, yes. So if you look at that, you have uh, beam structure. If you can see that beam structure, under beam structure, we have two conditions. One is local and one is global. Okay, meaning that all these inputs represent in the either local coordinate or global coordinate. If you can see that for thrust, okay, the local and the global might not be the same. Okay, if you can see that x prime is local axis, but x is global axis. So that directions are different. Okay, but in beam, okay, this x prime, y prime match. Okay, y and x, the local match the global. Therefore, the key prime, which is supposed to be local member stiffness matrix, is actually same with the global, oops, I cannot write, global member stiffness matrix. Okay, therefore only one template for you to use for beam. Okay, we will see further when you go to truss and frame later. Okay, so now since you only have this, okay, so I have to remind you that this is the global. Okay, we are talking about global member stiffness matrix. And coincidentally for beam, the local and global, the template are the same. Okay, I have shared you one link, I think Monday, I couldn't remember well the dates. Okay, if you are interested in the, how these values come in. Okay, there is a derivation documents for you to refer. Okay, so now let us look at this how to use this template. If you realize, if you can see, there are so many repeated items. 12 EI over L cubed, 6 EI over L squared, and this 12 still repeat, it start to repeat. Okay, 6 EI over L squared, yeah, repeated the circle. Okay, this is also 6 EI, and this is 4 EI. Okay, and you have 2 EI over L. So basically there are 4 items different in this matrix. You only need to determine the 4. Then you just pop in into this template. Of course, be careful of whether it is positive or negative. Okay, and there is one thing to let you know is this template is actually a symmetric form. So this, the one that I draw this line is a mirror line. Okay, where this actually mirror with this. Okay, if you can see that. Okay, so if you can see this, okay, is actually mirrored from here. This one is actually this one. Okay, so therefore you can write the half part only of this matrix is sufficient. Okay, so let's try for member one. Okay, so we only need to write these calculate these four items, right? So it needs the EI, it needs the length for member one. Okay, so if you have member two, if the EI and the length is different, so you have a different set of calculation. So let us see the length. Oops, it's not here. Let me check. 6 meter and 2 meter. So this is 6 meter and 2 meter. So now the 6 meter, put in 6 meter. The EI is given in the problem. So just put it in terms of the kilonewton, and the units used here is kilonewton and also meter. So you get this value. So what you need to do next? So you just refer to this template, 12 EI over L cube, put at the first K11. So this 12 EI, 2,400. So you put it the same with this template. So next K13 is negative, right? So the 2,400 negative is putting at K13 and so on. So maybe we put it another one. Okay, let's see. 2 EI over L is 14,400. Okay, so where is 2 EI? 2 EI is here. So you put in at this K24 here. Are you okay, class? Do you understand what I'm explaining here?
Yes.
Okay. Thank you.
Yes.
Yeah, basically, we are actually calculating the inputs for the template. Then this will be your member stiffness matrix. You need to determine for all the members. Okay, so it will be a very lengthy process, and you need, if you have a time constraint, you need to do it very fast because it is just a repetitive process. Okay, so then, of course, I will also advise all to do an Excel form, okay, to put in this matrix. Okay, then this will help you to verify your manual solutions better. Okay, so now we have done for the K1. Then we can move to the member 2, which we also name K2 here. Again, we find this 12 EI over L cubed, 6 EI over L squared, 4 EI over L, 2 EI over L. Because the length is different. The length now is 2 meter, but the EI are the same. Okay, so you just need to change this. Okay, length to 2 meter. Then you get a new set of this data. So these inputs you put in according to this template again. So you obtain the K2. Okay, so if you can see that K1 and K2 must be in this size, 4 times 4. Okay, and what does that mean? Okay, so you need to also know this. Okay, maybe this is bigger. Okay, this input is associated with near n, which is n. Okay, at the y direction. Okay, and this is the near n at the z direction. Okay, because in this beam you only have y and z. Okay, so and then you move to far end at y and far end at z. Okay, similarly for the vertical naming, near end at y, near end at z, far end at y, far end at z. Okay, so if you can see that this is why you have this numbering here. Okay, can we see how to give a numbering to this? Y5261, because it is following Y first and then Z at the near end, then Y first and then Z at the far end, following this numbering. So it will be for element number 2 right now. Okay, we are looking at element number 2. So it is from 5, 2, 6, 1. Okay, so can you tell me what is the numbering for element 1?
Four.
Yes?
352.
Yes, thank you very much. So it will from Y, then go Z from the near end, then Y to Z for the far end. So for element 1, it will be 4, 3, 5, 2. And then you name it again 4, 3, 5, 2. So once you have clear with this K1, K2, we need to form the structural stiffness matrix. Remember this one is member stiffness matrix. Okay, but at global. So now we want to form structure stiffness matrix. Again, this is at global as well. We don't talk about local axis, at global axis. Okay, so now we give it a big K, okay, to make sure that it's different from this small k. Okay, small capital K is about member, and now we need to form the big K. The size of the matrix will be following the total number of this structure DOF, okay, in your beam. So just now you have numbering your DOF until 6, D1 until D6. Therefore, your matrix size for this will be 6 times 6. Okay, so again, if I draw this line, okay, so this are actually the top triangle, okay, are actually can be mirrored down. Okay, you can have a look later, but you can put a note there that to remind you that is actually a symmetrical inputs in this matrix. But how to form this structure stiffness matrix? So if you look at this, I put the K1, K2, and the K here. The formula here is K1 plus K2. Okay, so therefore you need to have input from K1 and input from K2, okay, to form your structure stiffness matrix. I hope you can see now the one that I have highlighted in box. Okay, let us try to find how to find this number. Okay, so for example, I want to get the K22. K22 means that I'm referring to column number 2 and row number 2. So you need to go to all these K to search for whether they have column number 2 and row number 2. So now you go to K1 first, you found you have column number 2 and row number 2, the one that I have put in the box. Okay, then I continue with search in the K2, and I also found column number 2 and row number 2, and it's highlighted in the box. So now I just need to sum up these two values. Okay, then it will give you the one that in the structure stiffness matrix. Maybe not that clear. Okay, maybe we are going to try one more. Okay, why not we try K62 maybe. Sorry, K26. Okay, meaning that I'm referring to column number 6 and row number 2. So you go to K1 first. You go to K1, okay, and see whether you have column number 6. You don't have any column number 6 here. Okay, then you go to K2. Is there any column number 6? Yes, here, column number 6. Then I want row number 2. Column number 6 to row number 2. So I put a circle here. Okay, you see, you get the value here. So this is how you put this K1 sum up with K2 to form this structure stiffness matrix. Okay, now maybe I give you 2 minutes to try. Maybe let's try 5 K55. Can you try K55? Maybe I give you 2 minutes and see. Okay, class, can you get the value?
Yes.
Yes.
Okay,
Yes.
congratulations. Okay, so if the problem do not ask for the for you to find the structure stiffness matrix, you actually do not need to find every of these, I mean the complete matrix, 6 times 6 matrix. Okay, just find any value that will help us to solve for the unknown displacement only. Okay, what is that about? So let us have a look. Okay, before we go today, I think we miss out on the loading on the member. Remember, we shall not have any loading on our member. So if there is any loading on the members, we treat it as Q naught. Okay, how to treat it? We actually use the method of superposition to clear the loads and transfer them to the fixed end reaction. Okay, so for this case, this is element 1. Okay, this is element 2. So we will solve one by one. Okay, so for element 1, there is only one loading, so very straightforward. If you have other loading like on top of 32 kilonewton per meter, maybe there is another point load, or maybe there is 2-point load. So you need to add up this fixed end reaction. Okay, so I have selected the appropriate one for you to refer here. So maybe let us have a look on how to get this done. So you can start with naming this Q naught first. Okay, so how to name it? Just follow our naming this one. So for example, for element 1 is 4352. Okay. I might just go too far. Okay, 4352 here. If you can see that, we are just following the numbering of the DOF. 4352. So of course this is under Q naught. So you just name Q4 naught, Q3 naught, Q5 naught, Q2 naught. Okay, so how to get this value? This will be referring to WL squared over 12. Okay, because WL squared over 12 is about moment. So Q3 naught, and Q2 naught, okay, will be based on this formula. Okay, and then for this direction at at B, it is negative. Okay, so in this case, it directly show the positive direction here. Okay, so you get a positive. You can refer to this. There is no problem. Okay, then you will get a negative value. Okay, so if you start to confuse, then yeah, I don't know. Okay, but we just get with this. You must understand that why this is positive here. Okay, because the direction they have put in oppositely. Okay, so now for this Q4 node and Q5 node is a vertical reaction. So we'll be putting Q4 node, Q5 node using this WL over 2. So let us just try. W is 32, L is 6 meter and divide by 2. Then you get a 96 and they are both the same. Okay, so next Q3 node is using W L squared over 12. Okay, just a very straightforward template is given to you. Just pop it in. So you have a 96. And this is also 96, but actually is negative if you are following this direction. Okay, so now let us move to the element number 2. So we are referring to, can you see this? Cannot, it's hidden. Okay, wait. Okay, so better now. So now if you look at this element number 2, we have 48 kilonewton acting at the midpoint. So you refer to this where you are acting at the the point load are acting at the midpoint. So the M will be PL over 8. Okay, so it will be dealing with Q2 node and Q1 node. Okay, and the RA and RB will be dealing with the Q5 node and also the Q6 node. Okay, just put in this formula, like for example, this will be P over 2. So you get the 24. Similarly for 60, 6 node, Q6 node. And then for Q2 node, you are using the formula P L over 8. So P is 48, L is 2 meter, and divide by 8. Then you get the 12 kilonewton meter. Okay? So you get this done with all the inputs. You need to sum this up. Remember, this is we need to form the structure. Okay, not only the element. Okay, so now once you form it, the vector of Q naught will be matrix of size with 6. Okay, 1 times 6. Okay, so how to get this one? You go to number 1, Q1 naught. So where is Q1 naught? Is here. Q1 naught is 12 kilonewton. Let me circle it. Q1 naught. 12 kilonewton meter. Okay, but why this is negative? Anyone?
Direction.
Yes, because you need to know that the positive sign of this stiffness method is this one. These are all the positive sign. The one that opposite this, you get negative value. Okay, so that is why this is clockwise, but it will give a negative value. Okay, and you must know that moment the unit is kilonewton meter, and the translation forces, okay, it will be in kilonewton. Okay, x or y direction. Okay, so let's try another one maybe. How about 2? Okay, so Q2 node, there are 2. So I put it square maybe. So 96 and also 12. Okay, so this Q2 node is also moment. So why this is negative 96 plus 12 is because this is clockwise. Okay, and this is counterclockwise. Counterclockwise, positive. clockwise, negative. So this is how you get negative 84. So you continue with that to get the Q naught vector. Okay. Any question, class?
No.
Okay, I
No,
continue.
doctor.
Okay. So yeah, this is I would say long process. So maybe no hesitate during your process. It must be very clear what to do next. Okay, so that you can speed up. Okay, for the solution. So next, so this is not a whole complete matrices display. Not complete yet. If you can see that, it's supposed to have 6 times 6 matrix, right? But it has been taken out some of these unrelated, okay? But it's sufficient to show you what is the meaning of load displacement relation, because we are going to apply this formula, or you can say that this is the load displacement relations. This Q naught is also load, only this is a fixed end load, therefore we put it here at the back together with this D. Okay, so you need to place your vectors, your matrix K, and the vector D, vector Q, Q naught according to this equation. Okay, so then we can solve for this what we want to solve here. We want to solve D1 and D2 first. Okay, so therefore, if you can see that in your documents, you actually have this only. Very simple, 2 K2 by 2. Why this happened? Okay, maybe I need to go back to give me a page to explain a bit. Okay, so you need to use this Q equal to K D plus Q naught. Okay, this Q will have this 1 until 6. Let me draw it. 3, 4, 5, 6 equal to K will be in terms of 6 times 6. So it will have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then the D, vector of D, will be 1 times 6 size. 1, 2, 3, 4, 5, 6. So this is D, already. Maybe I will just put it here like this. This is Q. Then plus Q naught. Oops. Q naught will also in vectors of 1 times 6, 3, 4, 5, 6. Remember, we can put in the partition. Okay, partition to differentiate the unknown displacement and the known displacement. Okay, so just now we have unknown displacement D1 and D2, and the known displacement is 3 to 5, 3 to 6. So we can actually put a partition. Okay, so Q here opposite with the D, unknown will be at the bottom and the known will be at the top. Okay, Q naught will be all known lah. Okay, so I don't put it either is unknown or known. Okay, then similarly for this K, okay, you can also put in this into let's say this category is K11, this is K12, this is K21, this is K22. It's just a region. Okay, I don't actually set K11 is the first item. No, the region Okay, I can categorize into 4 regions here. Okay, so now in the stiffness method, we want to solve the unknown here. So if your dk is equal to 0, let's say this is all 0, 0, 0, 0. So remember your this how to say the multiplication of the matrix and vectors. Okay, the process is actually multiplying to get this qk done. You are actually forming something like this: k11 multiply duk plus k12 multiply with this dk. Can you know how to do the multiplication? This one multiply with this, okay, plus, and this one multiply with this. Okay, so you can see that k12 multiply dk, which is 0, will later be cancelled out, 0. So the one is meaningful here will be only k11. Okay, of course you need to plus q naught later at the back here. Okay, so meaning that you can, if the structure stiffness matrix is not the problem to be solved, okay, you no need to determine the whole 6 times 6 matrix. You need to only find the one that will help you to determine the DUK, the unknown displacement. Do you understand what I'm trying to tell you? We just need to find this K11 only, because finding K11 will help us to solve the unknown displacement. Okay, class?
Okay, Doctor.
Okay, unless there is a value in your this non-displacement. Let's say D6 has value. Okay, like for example, just now we have negative 0.002, let's say, for this D6. So therefore, then you need to create another, you need to determine as well this value of for this 6. Okay, we will have a look later to address the question B. Okay, but for this case, we are just need to putting this Q1, Q2, okay, and this is 1 and 2. Okay, we only need to solve for this structure matrix for these 4 items only. Okay, the one, if you can strategize early, okay, you no need to determine full of your member stiffness matrix, because at the end you only need these 4 data from your matrix. Okay, so now let us try to solve this 2 simultaneous equation. You can form it in terms of 2 simultaneous equation. Okay, or you can use your calculators to solve it. So how to do that? So this at 6400 will multiply with D1 to get this. Okay, plus this 43200 multiply with D2. Okay, you will get this. And then will be equal to, supposed to be equal to 0, and at the end is minus 12. So this minus 12 can be bring over to the other side here. Okay, then you get this first equation. Okay, similarly, the second equation will be 43200 multiply D1 plus 115200 multiply D2. Okay, and the negative 84 you can bring over the other side. Okay, then you form the second equation. So now you solve for these two simultaneous equation. You solve for D1 and D2. Okay, so means actually if you want to find the displacement, that's all your answer. Okay, so and you must be very clear what is the meaning of D1 and D2. Okay, D1 and D2 is the displacement that you highlight in your numbering. Okay, where Can I go back to? If you can see that, you are referring to this rotation at C and rotation at B. Okay, so actually you can put it here. So D1 is actually also rotation at C, and D2 is also equal to rotation at B. Okay, and the unit for the rotation is in radian. Okay, so you get the answer directly. Okay, once you solve this stiffness equation. Okay, class, are you okay? Are you still okay?
Okay. Yes.
Okay, I
Okay,
hope you can follow
doctor.
well. Okay, but after I explain this, I will, you can continue, okay, to study. If you have problem, you can rest again, okay, in your next class. Okay, but now we still want to find the support reactions, okay. So if you look at our this, I cannot change my pen color, can I? Oh, can. Never know that. Okay, let me change color now. Is it in color? Let me. Oh, yeah. Wow. Okay. So now I already saw for this DUK. So I know that the DUK is this value. Wow. Oops, it's not up to here. It's up to here. Okay, so you can place it to these equations or matrix, no problem. But now our concern here is QUK. How to get this QUK? So QUK is actually equal to K21 DUK plus K22 DK. Okay, so means that it will be this one multiply again, okay, with the DUK plus this K22 multiply with this, okay, the DK. Okay, so therefore, which one will you require? So it will be this item only. The K22 multiply 0 will get 0 later. Okay, unless you have some value here. So therefore, you just need to multiply each of these value. Okay, for example, this will be K31. Okay, don't confuse with this K21. This is just a region. Okay, K32. Okay, multiplied with D1 and D2. Okay, it will be K31 multiplied D1 plus K32 multiplied D2, and then plus Q3 naught. Okay, then it will give you the value of Q3. Okay, give you a value of Q3. Can you see that? Maybe I will write it here. If you want to get a Q3, it is actually K31 multiplied D1 plus K32 multiplied D2 and plus K33 multiplied D3 and so on here. Okay, K33, D3, so on. But this is all equal to 0 because D3 to D6 is 0. Okay, and lastly, plus Q3 naught. Okay, so then this is all known. So you can directly solve for the Q3. Similarly for Q4, Q5, Q6. Okay. So I don't show the matrix again here. Maybe the matrix is here. Oh, it's here. So if you can see that to get the Q3, okay, so it will be 0 multiplying D1. Maybe I just write it. Q3 will be equal to, I'm referring to this. Okay, and this. Okay, So Q3 will be 0 multiply D1. This is how you multiply the matrix and vector, plus 14400 D2, and supposedly there will be ons lah. Okay, but O is equal to 0. No need to show it. And plus Q3 naught. Q3 naught will be 96. Okay, then you get your Q3 value. Okay, you can continue until Q6. So what is Q3456? Again, you need to be very clear. Okay, you can go back to see this numbering. Q3456 is 34 is MA. This is MA. This is AY, and then it will be BY and CY. So you are determining for that. So once you know that you are determining for this, you will supposedly know the units. For moment is kilonewton meter. For forces, okay, it will be in terms of kilonewton. Okay, so now you have got your answer for support reactions. I would like to continue for some more. Okay, so what is the problem of B? I've forgotten. Wait. Determine the shear force and bending moment at joint B, only at joint B, if support C settle to mm. So meaning that we want to find internal force right now. Okay. Again, you need to determine the internal force, you need to solve for the displacement first, unknown displacement. Where am I? This one? Yes. Okay, we need to solve again for D1, D2 because the situation have changed. Because they have found that support C actually settled 2 mm. When support C settled, we deal with this support C and we deal with the vertical direction, 6. So D6 right now, you have a value. Okay, so therefore the D1 and D2 is not the same answer with question A because of this one. Okay, therefore you need to resolve it again, and you need to extract again for this column number 6. Why? Because your D6 row number 6 has a value of negative 0.002. So it is no more 0. You cannot eliminate that. You need to get this inputs, okay, to multiply with this negative 0.002. Okay, so this is how you do it. Okay, I will just quickly mention how to get the first equation. So it will be at 6400 multiplied with D1. Okay, multiplied with D1. Okay, and then 43200 multiplied with D2. And then negative 64800 multiplied with negative 0.002. So you just sum it up. So you get the equation number 1. Okay, of course, don't forget about the Q naught. Okay, similarly, you produce for the equations for number 2. Then you solve these two simultaneous equations, you solve a new D1 and D2. Okay, but now we don't want to find the support reaction, we just want to find the internal force. Okay, so what you can do here. So internal force, we use local stiffness equation. Just now, the Q equal to KD plus Q naught is in this big capital letter, right? KD plus Q naught. Okay, this is global. But when you want to solve for internal forces, this global solve for the displacement and also the support reaction. So for this local stiffness equation, which is right in the small letter, we solve for internal forces. So how to do that? Okay, we just establish the stiffness equations. How to get the Q? Because you want to find the B. The B is you can find the shear force at B through member 1 also can, through member 2 also can. Why? Because at B you are talking about this number 5 and number 2. Okay, so we just want to solve. I think I shall have this in my slide. Wait, wait, this. Okay, so now we are we want to find 5 and 2 only. The rest we don't want. Okay, so now 5 and 2, you can get it from element number 1 or element number 2. So now let's look at element number 1. Okay, so you just follow the Q according to this near end. Okay, near end Y, near end Z, and far end Y, and far end Z. Okay, this is how you name it. So it will be 4, 3, 5, 2. So now the Q will be named Q4, 3, 5, 2. Similarly for this Q naught as well, it will be Q4 naught, Q3 naught, Q5 naught, and Q2 naught. Okay, similarly for your D as well, it will be D4, D3, D5, and D2. Okay, so Q, I suppose you don't have any problem. Let us have a look on this K. What is this K? This K will be your member member stiffness matrix at local. So it will be equal to your K1. Okay, so you just refer back to your K1 page ago. Which one? Yeah, you just take this, everything. Okay, K1. Then about Q naught, you just need to take this. Okay, 4, 3, 5, 2. Okay. So remember you have a negative at Q2 naught. So how about D? D4, 3, 5, 2. So just now you have solved for D1 and D2. Okay, D5, D3, 4, 5 is 0. D6 is negative 0.002, right? So now you have 3, 4, 5 is 0. And Q2 will be referring to this one. Sorry, not Q2, D2. Okay, so you just place it back here. Then you have all this setup for the stiffness equation. You can solve it directly. Okay, how to solve it? So we can you don't need to solve all of this. You just need to solve for Q5 and Q2 because this Q5 will be the shear force at B, VB. Okay, this Q2 will be the moment at B. Okay, so how? Let us just try Q5 maybe. Q5 will be negative, why it become red? Negative 2,400 multiply 0. Oh, becomes 0. Negative 7,200 multiply 0 also 0. 2,400 multiply 0, 0. So it left only this. This one multiplied with this. Okay, so you get this. And then don't forget about the Q5 naught, 96. So you get the answer. Shear force must be in kilonewton and moment in kilonewton meter. Okay, class. You have any question for me?
No, doctor.
So, uh, I think somewhere must be something wrong here. Maybe you can help me to check. This member 2 must be same answer with this member 1. Okay, because for Q5 and Q2, they must get the same answer. Wait, why not the same? Please try. It must get the same answer. Okay, so I don't know why it's not the same. Okay, please check any error with this equation and this equation. Okay, I think that's all for today. Sharing or lecture. Okay, what I would like you to do is maybe to repeat solving this question, okay, and get prepared. Okay, then tomorrow we so that we can do the tutorial question together. Okay, class. If you don't have any question, I would like to stop. Yeah, I would like to stop recording now. Okay, and what I want you to do offline the remaining time is to redo